today, before we start, I want to have a little bit of a discussion about data and statistics, which will help you answer that last question in the Crystal Violet Lab. When we study data, we usually use very large population samples. So whenever you take a statistics class, I mean, they're talking about huge sample sizes, like thousands, hundreds of thousands, whatever, lots of data points. And when you talk about data, we always talk about the distribution of that data in something called the bell curve, right? You've heard of the bell curve? You've heard probably nightmares about how professors will curve to the bell curve. So sometimes if your score's too high, you can be curved down. Yeah, it happens. It happens to me. But it's not as bad as it used to be. They're a lot better at how they do that. Anyway, the data dead center on this, and this is kind of like a, and that's not very center, is it? This is basically what, when we were talking about those Maxwell distribution diagrams, the area under this curve is represented by numbers of data points, all right? So the curve could be skewed one way or the other. If everyone gets 90s, we're not going to have a normal distribution. We'll have probably a bigger hump here, and then it gets smaller toward here. All right, but anyway, this is your normal curve. So the middle here, what's represented here in the middle? The mean, right? So X bar. Now, when you calculate a standard deviation, what you're really doing is finding a number, and that number then can be added and subtracted from the mean. And statistically, the definition when standard deviation is applied, 68% of the data points falls within one standard deviation. So one standard deviation is a good, we're probably going to, if we run a lab and we take everybody's average, there's a high likelihood that our data singly would fall within one standard deviation. So it's pretty good data. The reason we look at this is we want to know, I know there's a lot of times you get a bad trial and you're like, I just want to, can I throw, you ask me, can I throw this data point out? It's just bad. I'm like, well, why? We can't just throw things out. So a lot of times we use this standard deviation, plus or minus one standard deviation, to be that limit. If you're not within a standard deviation, your point is probably pretty far from the mean. Okay, your point is far from the mean, so we probably can get rid of it. It is bad statistically. Sometimes we let people go out to 2 standard deviations. 2 standard deviations is a lot of freedom. It encompasses 97% of the data. So if you fall outside of 2 standard deviations, your data is really not good. And if you fall outside of 3 standard deviations, you just need to stop doing science, because that's like 99.5 or something. I can't remember. I thought it was a 97, 99. And these might be off a little, but they're both in the 90s. I know for sure about the 68% though. So that's what this lab is doing. You're going to take your data points and you're going to put them in L1 in your calculator. And so you have 4 data points. You're going to type those K's into L1. You can hit Stat, Calc, and then you do 1 var stats. What that means is 1 variable statistics. When that screen comes up, the first thing you're going to have is your mean. And you kind of need that. They want you to get the average, K. And then you're going to get, you're going to see 2 different kinds of standard deviation. You're going to see the lowercase s of x, and then you're going to see a capital S of x. Both of those are standard deviations. One's a little bit bigger than the other. This one here is the one that when you talk about standard deviation in math class, this is the one they're talking about. This is the standard deviation that applies to very large populations of items. In our class, even if everybody put in their data, it's still considered a small sample size. So we're going to use the larger one, the capital S of x. It's going to be a little bit bigger of a number than this, which is going to give us a little more freedom. It's going to give us more play here. So we'll have a little bit more latitude in whether or not our data is good or bad. And that is termed in statistics, it's got a degree of freedom included in it. All right? So I want you to find your standard deviation. You're not being graded on whether or not your data falls out of it or not, but I want you to say, hey, all my data falls within one standard deviation. Oh, no, my data falls outside of that. I know that you're going to have some because I know we had problems with the data. You're not being graded on that. You're being graded on your discussion of it, okay? So work on that problem and you can turn it in tomorrow. Are we good? All right. At any time from here on out, the reason I didn't talk about it yet is since we rearranged the curriculum, previously I'd done a lab where it was included in the discussion already, and I haven't done that unit yet, so I'm all out of whack because of the change in the order. All right, so let's talk about this. If I were to add water to this reaction, what would your normal inclination be about what happens when we add water to the no effect, right? Everything's diluted, so the ratio doesn't change. It actually does change. And so whenever you see an aqueous solution like this, and anything that has ions in it, and this is aqueous as well, this is the lab you did yesterday, anything that's aqueous is going to be affected. How it's affected depends on how many reactants and products that are aqueous that we have. So if I'm going to write, I just want to show you with the K expression. If I have FeSCN plus 2 over Fe plus 3 NSCN minus, and I dilute it, yes, I agree. Everything is going to be diluted the same amount. However, let's pretend we're cutting this in half. We're doubling the volume with water. That means we cut this in half, and it also means we cut this in half and that in half. So what happens mathematically to that denominator compared to the numerator? So it's decreasing even more, isn't it? Because we have two things being diluted. Do y'all see that? So if this denominator gets smaller, so both get smaller. This gets a little smaller if the concentration gets smaller if we dilute, but this gets even more smaller. So now we're at a Q value, and what happened? What is Q compared to K now? No. The denominator gets smaller, so Q is, compare it to K. Compare it to K, greater than K. Q is great. Does everyone see that? Do I need to show you the math? If everything has a concentration of 10 molar, all right, what is the K? 1 over 10, right? If I cut everything in half, what is the Q now? You see how now Q is bigger than K? All right. So if Q is bigger than K, for us to get back to equilibrium, what do we have to do? Q needs to get smaller. I mean, Q needs to get smaller. How does it get smaller? More reactants, which is what direction of shift? Left shift. Reactants, left shift. So this is not, left shift is not always going to be the answer. Because if I end up having 2 products and 1 reactant, the opposite would be true. Right? If I had 2 reactants, and you have to look at the exponents as well. You can't just look at the reactants, because if this were cubed or something up here, that would change it even more. So every single case is individual. You just have to look at it. And if I have the same number of products and reactants all raised to the same exponents, would there be an effect? No. So you have to look at each individual case. Does that make sense? Okay. The other problem we did, it was a bunch of gases, and if we add water. Well, if we add water in a container with a bunch of gases, that doesn't change concentration or pressure of the specific gases. When you add water to an aqueous system, it can, depending upon the ratios. All right? Okay, let's now go on with the original intent of this little lecture. I'll be done pretty quick. So here we have some diagrams, some energy diagrams that you all have seen more than once in your chemistry career. And these are the energy profiles that tell us if something is exo or endothermic. So we can relate this directly to K, generally. And it's pretty common. It's pretty interesting because it's looking at something a little bit differently. So let's say we have this first case. Case 1, our reactants are really high in energy and our products are low. Where did the energy go? It left. So what kind of reaction is this? Exothermic. All right. So I want to know in an exothermic reaction what my magnitude of K is, and I can figure it out from this. If I were to tell you, okay, you're going to run the hill, I want to know which way would you prefer to run the hill, the forward way or the backward way? The forward way. So what this little shorter hill is telling us, lower activation energy, so the forward reaction is more favored. If the forward reaction is favored, tell me about the magnitude of K. K would be greater than 1. Now this is generalized. There's always exceptions to things depending upon entropy. And that's something we'll learn when we get to thermo. But for now, usually an exothermic reaction means the forward reaction is favored and K is greater than 1. This, we have low energy reactants, high energy products. How did the products get there? They got energy from the outside, making this endothermic. In an endothermic reaction, we want to run the reverse reaction, don't we? The reverse hill. So if reactants are favored, what's the magnitude of our K? Less than 1. And in the last case, this is where we have a delta H of 0. There is no heat exchanged or lost, which pretty much means that K is equal to 1, generally. You're not going to see that very often. So are we good? Kind of understand this? All right. Last set of problems. So this is our relationship of thermo to equilibrium. Now we're going to connect kinetics to equilibrium, and I'm going to start with, we'll do this problem. Kinetics and its relationship to equilibrium. So I think it did come up in this classroom. Somebody asked me when we were doing rate laws, what happens if there's an intermediate in the slow step? What do you do? Today we're going to address that. So starting today, you're going to be responsible for identifying some problems. So this is a mechanism. You might get instructions that say, write the rate law. Do y'all not have this problem? Oh, okay. Just Gavin was doing a hunt, so I didn't. Got it. All right. So if I ask you to write the rate law with the knowledge that you know right now, what would you say? Go to the slow step. Rate is equal to K times the concentration of C. There's only 1 in the slow step, so it's C first order with respect to C. This is a problem because if you try to add these up and look at the overall, C is an intermediate. It gets crossed out and it doesn't show up in the overall. Why does that matter? If it doesn't show up as a reactant or as a reactant that's present or a product that's produced, how can I measure it in my world, in our scientists' world? We can't. We have to replace it with something. And so because the previous step is an equilibrium step, there's a proportionality, thanks to the K, between these two guys. So I can redefine C's concentration in terms of something I can actually measure. So to do that, I'm going to go to that slow step, and you can do it on the side. I'm going to write the K expression from the slow step, from the equilibrium step, which is products over reactants. So I'm going to have C concentration divided by A times B. All right? Now remember, what's our culprit? Who's the thing we want to replace? C. I want to get rid of that. So I'm going to rearrange this equation to isolate C by itself. So I'm going to multiply this each side by AB. So I get KC times A times B equal to C. Okay? All I do is take this guy right here, which is equal to C, plug him into C. So my rewritten rate law is rate is equal to K, that's the original K, times this KC that we have, times A times B. Now, we're not cheating here because we're not going to actually do math with these K's, but what is a constant times a constant? Another constant, all right? So we are going to combine these. You're not going to ever do it because mathematically they might be the same. We can figure them out from each other, but they have totally different units. All we're going to say for our purposes is, okay, this makes a new constant. If you have to call it something different, call it K prime. I'm okay if you just write K. It's a new K times A times B. And that's our new rate law. Do you have any questions? Okay. We're going to work a couple more. All right, let's try this next one with the NOBRs. Let's do this one. Okay. And again, you're not going to have a heading, this one needs an equilibrium substitution. You're going to have to figure that out by looking at your original rate law. From here on out, either one can show up, a non-substitution one or a substitution one. So rate then is equal to K times, what's the slow step? What are my reactants? NOBR2 times NO. So that is my normal, what we expected rate law to be. Does anyone see a problem? NOBR is an intermediate. I can't measure that. So I need to redefine. Whoa, I just wanted to erase. I thought my finger was an eraser. I just now want to redefine what my NOBR actually is. So I go to the fast equilibrium step, and I write K is equal to KC is equal to products NOBR2 over reactants of NO times BR2. And now what do I do? But what am I trying to do? What's the isolate? I want to get this NOBR2 by itself because that's the thing that needs to be replaced. So I'm going to cross multiply. I get KC times NO times BR2 is equal to the culprit intermediate of NOBR. Okay? There's a proportionality between those two based on the new combined Ks. So I'm going to plug that in. I get rate. Are you guys okay if I combine my Ks at this point? K prime times NO times BR2 times NO. I can definitely clean this up, so what would I do? Yeah, we have NO to the second times BR2. And that would be my rate law. Okay? Let's do one more real quick because it's going to bring up something that is important. And that something is talking about fractional coefficients and why they exist, because it doesn't make sense to have a fractional coefficient. So rate law, how we expect the rate law to be, rate is equal to, you go to the slow step, K times BR to the first times H2. Do I have a problem? Yeah, I do. my bromine is not supposed to be there. That is an intermediate. I got to get it out of my rate law. So I'm going to go to the equilibrium step. My Kc is equal to Br squared divided by Br2. That's just the equilibrium constant. I'm going to isolate my Br, and so we get Kc times Br2 is equal to Br squared. Can I plug in Br squared for Br here? No. What do I have to do? Square root. So that makes me Kc. I'm just going to square root them separately. Br. What's another way to write square root, though? Yeah, to the 1/2. So what I'm going to plug back into this is rate. I've got a K and a K, that makes a K, times Br2 to the 1/2 times H2. So I've always said what order was. What is the literal meaning of order? Order is what? How many of those molecules are in the rate determining step? So an order of 1, 2, 3 makes sense. An order of a 1/2, you can't have a 1/2 a molecule. No, you can't. So when you see a 1/2 like that, you know that an equilibrium substitution was done, because it's not the literal 1/2 molecule of Br2. It means that 1/2 of that concentration is proportional to the original molecule that was in the step. All right. So if you see an exponent, that's a fraction. That's where it came from. It doesn't mean there's a 1/2 a molecule in the rate determining step. It doesn't mean that. All right. Any questions on this? Yeah. Right. If I take the square root of the speed of light, it's still going to be a constant, right? Yeah, it doesn't matter. Constants, and we're not going to that level. We're not going to be manipulating those. You're just going to have to be able to write rate laws. Okay? There would be a lot of nasty work required to get those Ks to a place we could combine them mathematically. It would be a unit nightmare. All right, I think that's it for the day. Go ahead and clear off your desks.